All right, so today we are going to work two example problems, the first of which will illustrate how to handle a critically damped RLC circuit, and the second of which will illustrate how to deal with dependent sources in RLC circuits. So let's start with our critically damped circuit. So the circuit we're going to look at is this guy here, where we have a 4 milliamp source connected in parallel to a 1 ohm resistor. Then we're going to have an inductor L here. We're actually going to figure out what the value of this inductor is that will force our circuit to be critically damped. Here we have a switch that is opening at T is equal to 0. We have another 1 ohm resistor down here. A 5 ohm resistor here. And a 1/2 farad capacitor here. Our critical pieces of information to determine will be our capacitor voltage, Vc of t, our inductor voltage, VL of t, and our inductor current, I of t, which will be common to our series RLC circuit during the transient condition. Our quantity of interest is this voltage, which I'm going to label Vx of t, which can be thought of as the voltage drop over the 1 ohm resistor to its right, or the voltage drop over the 4 milliamp current source to the left. So our first step, as always, is to look at the circuit during the transient condition as a dead network to determine whether, to calculate alpha and omega naught and determine whether the system is critically damped, overdamped, or underdamped. So our dead network representation of our circuit is going to have our current source open circuited. We are going to have a 1 ohm resistor here, our inductor L here, during the transient condition, our switch is open, so that's why we have an open circuit in that branch. Here we have our 5 ohm resistor. Here we have our 1/2 farad capacitor. And so we can see that this is a series RLC circuit where our equivalent resistance R is 1 ohms plus 6 ohms. Our equivalent inductance L is to be determined, and our capacitance C is equal to 1/2 of a farad. Okay, so in order to determine the value of L that will cause critical damping, we need to understand that critical damping occurs when alpha is exactly equal to omega naught. So in this case, since we have a series RLC circuit, alpha is equal to R over 2L, and omega naught is equal to the square root of 1 over LC. And so now we're going to set these two things equal to each other and do some manipulation here, right? So if I say that R over 2L is equal to the square root of 1 over LC, what I can do is square both sides to get rid of that square root sign. So that's going to give me r squared over 4l squared is equal to 1 over LC. I'm going to multiply both sides by L squared, which is going to give me R squared over 4 is equal to L squared over L, which is going to look like L over C. And from here, if I multiply both sides by C, I find out that my inductor value L needs to be 1/4 of R squared C in order to force our system to be critically damped. So if I plug in my value, I'm going to have 0.25 or 1/4 times R, 6 ohms squared, times C, which is 1/2 of a farad. And I find out that my inductor value needs to be 4.5 henries in order to make this circuit critically damped. Now I'll simply plug in my values. So R6 over 2 times 4.5 is 2/3 meters per second. And just to make sure I've done my algebra correctly, the square root of 1 over 4.5 times 1/2 also comes out to be 2/3 radians per second. Since alpha is equal to omega naught, we have a critically damped system. All right, so now that we've determined the shape of the response, we will analyze the circuit at t is equal to 0 minus. So at t is equal to 0 minus, our circuit is at DC steady state, which means we are going to replace our inductor with a short circuit, where we'll replace our capacitor with an open circuit. And because we are at a time prior to the switch opening, we're going to treat our switch as a short circuit. So putting all of that together, we have 4 milliamp source in parallel with a 1 ohm resistor. Our inductor looks like a short circuit, so that's that. Our switch is closed, so our other 1 ohm resistor is connected directly in parallel. Here we have our 5 ohm resistor. And then our open circuit representing our capacitor. And I'm going to label my quantities of interest, which include VC at 0 minus, VL at 0 minus, and I at 0 minus. So let's start with the easiest quantity. VL of 0 minus has to be 0 volts because it's the voltage drop over a short circuit. Our quantity I at 0 minus is also pretty easy to determine. Our 4 milliamp source sees 2 1 ohm resistors in parallel. So the amount that splits off to the right and flows through the right 1 ohm resistor has to be 2 milliamps. And from that, our voltage VC at 0 minus is going to be 1 ohm times 2 milliamps, which is, of course, 2 volts. So here's our circuit analysis at t is equal to 0 minus. Now we'll move along to what's going on at t is equal to 0 plus. At t is equal to 0 plus, our switch is now open. We are going to represent our inductor with a current source having the same direction and current as I at 0 minus. Let's get to that real quick. So I at 0 minus was directed to the right, and it had a value of 2 milliamps. So we replace our inductor with a 2 milliamp current source, direction right. Our switch is open. So effectively, the right 1 ohm resistor is no longer going to influence the behavior of the circuit. Here's our 5 ohm resistor. We're going to replace our capacitor with a voltage source having the same polarity and magnitude as VC at 0 minus, which was 2 volts. And now identifying our quantity of interest, VC at 0 minus has to be 2 volts. I know it's a bit redundant, but I like to keep track of it. I at 0 minus is 2 milliamps. And our last quantity of interest is going to be VL at 0. Sorry, all of these are at 0 plus. My apologies. So I at 0 plus is 2 milliamps because the inductor current cannot change abruptly. VC at 0 plus is 2 volts because the capacitor voltage cannot change abruptly. And the only thing that we're missing here is the quantity VL at 0 plus. In order to get that, there are a couple of different things that I could do. I'm going to choose to do a source transformation on the practical current source on the left-hand side of my circuit. So instead of having a 4 milliamp current source in parallel with a 1 ohm resistor, I'm going to draw this as a 4 milliamps times 1 ohm. So that's 4 volts voltage source in series with a 1 ohm resistor, obeying the rules of source transformation where I place the positive polarity terminal of my voltage source on the same side as the head of my arrow for my current source. Now I have my 2 milliamp resistor, my 5 ohm inductor, excuse me, my 5 ohm resistor, and my 2 volt source. And this is my voltage VL at 0 plus. And I'm going to get this just using Kirchhoff's voltage law. So I'm going to have negative 4 volts plus 2 milliamps times 1 ohm, where I'm assuming that my 2 milliamps of current is going to flow into the positive polarity terminals of my resistor. Then I'll have plus, stylus will write, VL of 0 plus, my quantity of interest, plus 5 ohms times 2 milliamps plus 2 volts is equal to 0. And now I'm going to put VL at 0 plus on the left-hand side of the equal sign, and I'm going to move all of the other terms to the right. So when I move negative 4 volts to the right of the equal sign, it's going to look like positive 4 volts. Then I'm going to have 2 milliamps times 1 ohm. So that's 2 volts, positive 2 volts move to the right-hand side, looks like minus 2 volts. Positive 10 volts move to the right-hand side, looks like negative 10 volts. And then another positive 2 volts move to the right-hand side, looks like minus 2 volts. So we have 4 minus 14 is negative 10 volts. And so VL at 0 plus is negative 10 volts. Finally, I'm going to have to analyze my circuit at t is equal to infinity because there is a independent source left in my circuit at t is equal to infinity. So at t is equal to infinity, My switch is open and I am at DC steady state. So I have 4 milliamp source parallel with a 1 ohm resistor. My inductor looks like a short circuit. Here's my 5 ohm resistor. My capacitor looks like an open circuit. All right, let me identify my quantities of interest. So V, C at infinity, L at infinity, I at infinity, VL at infinity must be 0 volts since it's a voltage drop over a short circuit. I at infinity must be 0 amps here because all of the current that's leaving the 4 milliamp source will flow through the 1 ohm resistor on the left that is actually connected to the 4 milliamp source. Beyond that 1 ohm resistor to the left, we don't have any closed current carrying paths, so no current can flow down that path. Using Kirchhoff's voltage law, around this loop, we can see that the capacitor voltage VC at infinity will be the same as the voltage drop over the 1 ohm resistor on the left. And so from that, VC at infinity is going to be 4 milliamps times 1 ohm, or 4 volts. All right, so we're now at the point in our analysis where we will start applying our response equation to determine the behavior of things. So what I'm going to do really quickly here is scroll up to the top of the problem so that we can identify the most efficient route to determine our quantity of interest. So our quantity of interest is the voltage Vx of t, or the voltage drop across the 1 ohm resistor on the left. This current, which I'm going to call Ix of t, will be easily determined if we know our inductor current I of t, by saying that Ix of t is simply going to be 4 milliamps minus I of t, and Vx of t simply 1 ohm times Ix of t. So we are going to use our response equation to determine our inductor current I of t, as this will allow us to calculate the voltage Vx of t with the least amount of work. Another possible way that we could do this would be to add the inductor voltage plus 5 times the inductor current plus the capacitor voltage together. But that is going to involve a significant amount of more work than simply finding I of t and using KCL and Ohm's law. All right. So in a critically damped circuit, our current I of t, which is the inductor current, so that's why I'm now denoting it as IL of t, will be of the form A1 t e to the negative alpha t plus A2 e to the negative alpha t plus IL at infinity. Just to make sure, I'm going to pop over here to my table, and I'm using this relationship right now. Looks like I've transcribed everything correctly. We already know what alpha is, so we don't need to do any other manipulation of this guy or determine any other quantities. So at t is equal to 0 plus, this is going to look like, so this t right here makes this whole first term go to 0. This e to the 0 goes to 1. And so we're going to have A2 plus IL at infinity. Rearranging slightly, we can say that A2 is IL 0 plus minus IL at infinity. IL of 0 plus was 2 amps. IL at infinity was 0 amps. So this looks like 2 amps. Now we're going to use our derivative-based relationship. So recall that the voltage drop across an inductor, VL of t, is given by L di by dt. So this is going to look like L, and now I'm looking at my table, and I'm just going to be putting in this relationship. Negative alpha A1 t e to the negative AT plus A1 minus alpha A2 e to the minus alpha t. At t is equal to 0 plus. This term is going to go away. This term is going to go towards 1. And so what we're going to have is simply L times A1 minus A2. So from this, we can say that A1 minus A2, where is equal to VL 0 plus divided by L, or A1, which is what we're trying to find, is going to be VL of 0 plus. So that was negative 10 volts divided by our inductor value, which was 4.5 henries, plus A2, where we found A2 to be 2 amps in a previous step. So A1 comes out to be negative 0.222, or negative, 2/9 of an amp per second. From this, I of t is given by negative 2/9 t e to the negative alpha 2/3 t plus 2 e to the negative 2/3 t plus 0. Actually, there's a significant mistake here, and the mistake that I've made is with the units. So that should have been 2 milliamps here and 2 milliamps here, which is going to change this significantly, right? So I apologize for that. That's going to change this guy. So negative 10 over 4.5 plus 2 times 10 to the minus 3 comes out to be negative 2.220 amps per second. Plus 2e to the blah, blah here, and this is going to be milliamps. If we didn't do that, when we simulate this, we would be getting the wrong result. The next thing we would do is recognize that current Ix of t, the current flowing down through the 1 ohm resistor, is simply 4 milliamps minus I of t. So that's going to be negative 2.220 t e to the negative 2/3 t amps plus 2e to the negative 2/3 t milliamps. Actually, let me make sure I'm getting my signs right here. So the 4 milliamp should be a positive sign. Since I'm subtracting I of t, I should change the sign on both of these. And finally, Vx of t is simply 1 ohm times Ix of t. So that's going to look like 2.220 t e to the negative 2/3 t volts minus 2e to the minus 2/3 t millivolts. I just realized, sorry, let me scroll back a bit. I just realized that I've been doing the most trivial of math incorrectly this entire time. And so what I mean by that is 1 ohm times 2 milliamps is not 2 volts, it's 2 millivolts. And things like that. So I've been making these trivial mistakes the entire way through that I need to fix. I apologize for that. So let's fix that. So 4 milliamps times 1 ohm should look like 4 millivolts. Wondering why the scales came here. All right, so this is going to be 4 millivolts minus 2 millivolts, 10 millivolts, 2 millivolts. So this is going to look like negative 10 millivolts. Just double checking everything here. Only error here, just changing that millivolts. No error here. There is an error here, in as much as that should be millivolts, which is going to rechange this. So this is going to be -2/9 of a milliamp. Okay. So -2/9. Both of these are in milliamps. All right, there's going to be milliamp per second. These are in milliamps. All right, sorry about that. Okay, so now we're going to have 2/9 t e to the -2/3 t -2 e to the -2/3 t plus 4 millivolts. All right, I know I went through and I made a significant amount of corrections here at the end because I messed up the units on things. So let's simulate our circuit to make sure we corrected things appropriately. So let's bring up a new thing here. I want current source direction up. I want it to be 4 milliamps. Parallel with this, 1 ohm resistor. I'm not going to bother drawing the second 1 ohm resistor in our circuit because it isn't actually connected during the transient condition. So it's not providing any useful function. I'm putting the ground node on the negative polarity terminal of my capacitor. Right, and let's label some things here. So this is going to be our node BC attached to the positive polarity node of our capacitor. I'm also going to put a node Vx attached to the positive polarity terminal of our voltage source, or excuse me, our quantity of interest Vx. I need to put in my values for my resistor. So that's a 1 ohm resistor there, 5 ohm there. Our inductor we found to be a 4.5 Henry inductor. Capacitor was a 0.5 farad capacitor. Our initial conditions. We had 2 millivolts on our capacitor, if I'm not mistaken. Let's go back and double check that. Yeah, so at 0 minus, we had 2 milliamps times 1 ohm is 2 millivolts, okay? Initial condition on our inductor was 2 milliamps. And let us simulate. Let's see, alpha in this case was 2/3. Let's look at it for, let's start with 5 seconds and see how things go from there. And we're going to plot Vx as a function of time. All right, and now I'm going to type in my expression. So I'm going to add a trace, -2/9 times 1e to the -3, because I want it to be in terms of milliamps, times time times exp -2/3 time. Actually, that should be positive. Minus 2e to the -3 times exp -2/3 time plus 4e to the -3. So the scales are the same, but the waveforms don't match, which means I've made a mistake somewhere, which happens from time to time. So the first thing I want to do is make sure that I've typed in what I'm supposed to be typing in here, and I have all my parentheses closed correctly. So 2/9 times 10 to the -3. So effectively 2/9 of a milliamp per second times time. Let's scroll down here to the bottom. All right. Double check that my alpha was indeed 2/3. Yes, it was. Where is I just want to see something here. All right. So let's just go back and check through everything here. So I believe this bit to be correct. At t is equal to 0 minus, VL has to be 0. I must be 2 milliamps because the current is dividing evenly between the two 1 ohm resistors. And then we have 1 ohm times 2 milliamps should look like 2 millivolts as our capacitor voltage. Okay. At t is equal to 0 plus, our inductor current cannot change. Our capacitor voltage cannot change. So the only possible mistake I could have made here would have been in my Kirchhoff's voltage law equation, -4 millivolts plus 2 millivolts plus VL plus 10 millivolts plus 2 millivolts is equal to 0. So that sign changed correctly, that sign changed correctly, that sign changed correctly, that sign changed correctly. 4 minus 2 is 0, minus 10 is -10 millivolts, okay? T is equal to infinity. We have this circuit. All 4 milliamps that are leaving the positive polarity terminal of my current, or leaving the current source, have to flow down through my 1 ohm resistor. None of it can branch off and flow through this 1 ohm resistor because it's not part of a closed current carrying path. None of it can branch off and flow through this 5 ohm resistor because it's not part of a closed current carrying path. From that, I at infinity has to be 0. Since the voltage drop over the 5 ohm resistor is 0, when we do KVL around this loop, the voltage drop across the capacitor of 4 millivolts should simply be the voltage drop over the 1 ohm resistor. 4 milliamps times 1 ohm looks like 4 millivolts. All right. So all of our circuit analysis seems okay. When t is equal to 0, our first term goes to 0. When t is equal to 0, our second term, the exponential goes to 1, so we're just left with A2. IL at infinity is a constant value. So we have IL at 0 plus is equal to A2. 2 milliamps minus 0 is equal to 2 milliamps. Kind of hard to mess that up, okay? And make sure I used the correct expression here. Negative alpha A1T e to the minus alpha t. Negative alpha A1T e to the minus alpha t. I see the mistake. It should be A1 minus alpha A2. Okay, great. Found the error. All right, let's try this again. Negative 10 times 10 to the minus 3 over 4.5 plus 2/3 times 2 times 10 to the minus 3. All right, so this should be -8/9 of a milliamp per second, which is going to change this to 8, this to 8, and this to 8. And now they match. Wonderful. Okay, so this is a perfect illustration of how you can use LT Spice to make sure that you did things correctly. That one small mistake that I had there, forgetting that alpha, changed the output waveform enough to know that I had to make a mistake at some point in my analytical solution because it was not matching my simulation. Okay. All right, so what I'd like to do now is work another example problem, and I'll try to not play as fast and loose with the units here and see if we can get through this without making mistakes. So this particular example problem is actually one of your homework problems. It's from homework set number 7, problem number 4, and it contains a dependent source, which we have not yet addressed in this class. Okay. So our circuit of interest is this guy here. We have a 9-volt source. We have a switch that is opening at t is equal to 0. We have a 2 ohm resistor through which a current I'm labeling IA flows. We have a dependent source here, positive polarity on left, negative polarity on right, that creates a voltage of 3 IA. Then we have a 7 ohm resistor, a 25 millifarad inductor, and a 25 millifarad capacitor, and a 40/9 Henry inductor. So the quantities that we're going to need to pay specific attention to are our inductor voltage VL. Actually, hold on. Sorry, I'm a brain fart here. Let's call this voltage V, and it'll represent both the capacitor and the inductor voltage. Here is our inductor current, IL of t. Here's our capacitor current, IC of t. And our ultimate goal here is to determine an expression for IA. Okay. So our first step will be to look at this circuit as a dead network during the transient condition in order to determine whether it is critically damped, overdamped, or underdamped. So as a dead network during the transient condition, our 9-volt source is going to be turned off. Our switch is open during the transient condition, so that's why I have that open circuit. I have my 2 ohm resistor carrying some current IA, which is the controlling parameter for this dependent source. All right. So pretty easily, I can say that my capacitor value for this parallel RLC circuit is 25 millifarads, and the inductor value for this parallel RLC circuit is 40/9 henries. What is harder to determine is our equivalent resistance. So what we are going to do is we are going to determine the Thevenin equivalent resistance seen by our energy storage elements, the capacitor and the inductor. So we disconnect the capacitor and the inductor. So here are the terminals where the capacitor and the inductor were connected. I'm going to redraw the rest of my circuit. Like so. I'm leaving off the open circuited left-hand short circuit because it's not actually doing anything. And what I'm going to do now is I'm going to apply the test source method in order to determine the equivalent resistance of this network. Anytime I have a dependent source and I want to find the equivalent resistance directly, it will require me to use the test source method. So I have two options. I'm going to connect a source here. And what I need is this voltage V test and this current I test, because the Thevenin resistance RTH is simply the ratio of V test over I test. Now the question here is, do I use a current source as my test quantity or a voltage source as my test quantity? We can get the correct answer using either, but this particular circuit lends itself to using a test current source. The reason, actually, let's just make it 1 amp. The reason why I'm using a test current source here is because now I know that IA is just 1 amp, because this is a single loop circuit, okay? So applying Kirchhoff's voltage law, I can see that negative V test plus 7 ohms times 1 amp minus 3 volts per amp times 1 amp. So I'm just giving that 3 the correct units for a voltage, excuse me, for a current controlled voltage source. Then I'm going to have plus 2 ohms, 1 amp is equal to 0. From this, V test is going to be 7 volts minus 3 volts plus 2 volts is equal to 6 volts. And our equivalent resistance RTH is 6 volts over 1 amp is 6 ohms. From this, alpha is equal to 1 over 2 RC. So 1 over 2 times 6 times C, which was 25 millifarads, comes out to be 10/3. Omega naught is the square root of 1 over LC. L was 40 over 9 times 25 times 10 to the minus 3. So this comes out to be 3 radians per second. Since alpha is greater than omega naught, this circuit is overdamped. And from here, we'll simply go through and apply our overdamped relationships, right? We can treat this as if it were any parallel RLC circuit at this point. Okay, so at t is equal to 0 minus, our switch is closed. At 0 minus, we're at DC steady state, so our capacitor looks like an open circuit. Our inductor looks like a short circuit. So let's identify our quantities. So this is IC at 0 minus, IL at 0 minus, V at 0 minus. Pretty easily we can see that IC at 0 minus has to be 0 amps because there can't be any current flowing through the short circuit that's representing the capacitor. By Ohm's law, we can see that IA at 0 minus is 9 volts over 2 ohms is 4.5 amps. And why that is important is it will allow us to determine IL using Kirchhoff's voltage law. Okay, so applying Kirchhoff's voltage law around this loop I've outlined in green here. We're going to have negative 9 volts plus 3 IA. This is 3 volts per amp. Plus 7 ohms times IL at 0 minus equal to 0. So let's see, from that, IL at 0 minus is going to be 9 volts minus 3 times 4.5, so that's 13.5 volts, all divided by 7 ohms. That's negative 4.5 over 7, or negative 9 over 14 amps. So that's IL at 0 minus. And now we need V. Well, V at 0 minus has to be 0 volts because it represents the voltage drop over the short circuit that is the inductor. Okay, so we have our 3 parameters of interest, IC, IL, and V at 0 minus. Now we'll move along and analyze the circuit at 0 plus. So our 9-volt source is now disconnected. Here is our 2 ohm resistor through which our current IA at 0 plus will flow. Our capacitor is going to look like a short circuit because we need it to be a 0-volt source. And our inductor is going to look like a current source that's carrying a current of negative 9/14 of an amp. Like so. So here's IL at 0 plus. Here's IC at 0 plus. Here's V at 0 plus. We know that V at 0 plus has to be V at 0 minus or 0 volts. We know that IL at 0 plus has to be IL at 0 minus or negative 9/14 of an amp. And we can see by inspection that IC at 0 plus is going to be positive 9/14 of an amp. So some of you may be asking yourself, well, why isn't the dependent source going to contribute to the why doesn't the dependent source contribute to the current flowing through that short circuit? So recall that this current IL, when it's flowing this direction, sees this path up, which has no resistance, and this path to the left, which we determined earlier has an equivalent resistance of 6 ohms. So it will all flow through the short circuit. None of it will flow through the 6 ohm equivalent resistant path, which means IA is 0, which means the dependent source does not actually provide any voltage in this case. All right. So our analysis at t is equal to 0 plus is finished. We do not need to analyze this particular circuit at t is equal to infinity because there are no independent sources left in. So we're ready to apply our response equation. Okay. So let's talk about what we are going to do to determine that. I would argue, since our ultimate goal, let's scroll back up here to the top, is to determine this current IA, I would argue that our most efficient way to do this is actually to determine our capacitor voltage V of t. And the reason why I say that is because our voltage V of t divided by the equivalent resistance of 6 ohms will get us our current IA. If for whatever reason, when you are doing this problem as a homework problem and you don't feel comfortable with that, what you could instead do is to determine IL and IC and apply Kirchhoff's current law at this node to find that IA is just negative IC plus IL quantity. and you will actually get the exact same result. I'm going to do it the easier method because I know that it works. So I'm going to find V of t and simply divide it by 6 ohms. All right, so since this is an overdamped circuit, V of t, and in this case, we're going to be treating it as a capacitor voltage, will be of the form A1e to the S1t plus A2e to the S2t. There will not be a plus V at infinity term because the infinity term is 0 by definition, since there are no dependent sources or independent sources left in the circuit. So we need to calculate S1, which is negative alpha plus the square root of alpha squared minus omega naught squared. And we'll also need to calculate S2, which is given by negative alpha minus the square root of alpha squared minus omega naught squared. So I'm just going to throw this into my calculator real quick. So alpha was 10/3, so negative 10/3 plus the square root of negative 10/3 squared minus 3 squared. That to be negative 1.880. And negative 10/3 minus the square root of negative 10/3 squared minus negative 3 squared comes out to be negative 4.786 per second. At t is equal to 0 plus, we're going to have Vc of 0 plus is equal to A1 plus A2, which means A1 plus A2 is equal to 0. Now for our derivative-based relationship, we know that IC of t is C dV by dt. So that's going to look like C times S1 A1 e to the S1t plus S2 A2 e to the S2t. IC 0 plus reduces to C times S1 A1 plus S2 A2. And from here, we will have C times S1. So C was 25 millifarads. Negative 0.047 A1. And then we're going to have C times S2. Which is going to look like negative 0.00427 A2 is equal to IC at 0 plus, which was positive 9/14 of an amp. So here's equation 1, here's equation 2. I'm going to solve these guys simultaneously. So my coefficient for A1 in my first equation is 1. My coefficient for A2 in my first equation is 1. My constant term is 0. My coefficient for A1 in my second equation is negative 0.047, which I've saved as variable C in my calculator. My coefficient for A2 in my second equation is negative 0.00427, which I've saved as D in my calculator. My constant term is positive 9 over 14. And when I solve this, I get 15.041 volts. And A2 is, excuse me, negative 15.041 for A1, positive 15.041 for A2. From this, my voltage C of T is negative 15.041 e to the minus 1.880 T plus 15.041 e to the minus 4.786 volts. And IA of T is simply VC of T over 6 ohms. Or negative 2.507 e to the negative 1.880 T plus 2.507 e to the minus 4.786 T. I don't think we have enough time to simulate this because we only have 2 minutes left of class. You guys will be working this problem and I'm expecting you to simulate it as part of your homework anyway. So anyway, today we covered a critically damped RLC circuit, and once I corrected all my unit-based mistakes, things came out pretty okay. And then remembered to include an alpha. And then we worked a problem that contained a dependent source. What we are going to do for the remainder of this week, while we'll be wrapping up transient analysis of RLC circuits, we'll be looking at general RLC circuits. So what we're going to look at specifically on Wednesday is a circuit that contains a single inductor, a single capacitor, and some combination of resistors such that the circuit is not simply a parallel RLC circuit or a series RLC circuit. And then what we're going to look at on Friday is a circuit that contains 2 inductors or 2 capacitors that cannot be combined into a single equivalent capacitance or inductance, so that we have a 2 energy storage element system that behaves like a general RLC circuit. All right, that's enough out of me for today. So I will see you all on Wednesday.